well, it's a code equation. So can we do the same thing with my original problem, the Brownian bridge problem? Remember, we had an anticipating version of that problem, and we didn't know what to do with it. Right? So the how do we make it? Well, the idea would be, again, the u, the control is really constant, and if you conditioned that value, that constant, on which depends on the constant that depends on the end position. But if we condition it on the filtration, the knowledge up to time t, then we should get something that's adapted. But it's not easy to figure out what to do, figure out what would do that. But here's an interesting way we might proceed with that. And I'm going to have to go back. Okay, so it is, let's take the, so the problem is, well, for example 2, what we could do is we had an initial value for the x, we could let it evolve. We had an end value for the u, and so we kind of had to work backwards. We had to find something that would get me there, right? But those were two separate equations that we could one forward, another one backwards. The problem with this problem, the Brownian bridge problem, is that we have both the start and end value for the x, and nothing determined for the u. But here's a way you can visualize what's going on. And that is, if I go back to the example 2 problem. Okay, if I wanted to guarantee, for example, that so I have a starting point, starting value. If I wanted to guarantee that I get, say, to xb gets to 0 at the end, what I could do is, let's just make r really big, right? Because the bigger the cost I put onto r, the more likely, the closer this solution is going to be to, it's going to want to avoid anything but 0 at the end. And you can actually, and that's just a heuristic explanation of what's going on, but by making r very big, we kind of force the x to be small. We can get it close to 0. And so going back to my solution I had for here, it says if I pick the solution from example 2 and let r go to infinity, so that was actually here, right? So you see what happens when r goes to infinity. Some of those terms just kind of become unimportant. But there's actually, we see in the u, particularly here, the r's in top and bottom, right? So you actually can isolate. We can look at the limit as r goes to infinity, and that will give us potential, probable even u to work with. Well, if we're lucky, and we are lucky enough because it does work, and what happens is we get exactly this pair by making this, looking at that limit. And what we find is that in fact this is the adapted like we wanted to have, because it only involves the integral up to time t, and it satisfies the relationship we need to satisfy here. So this is also sometimes referred to as Brownian bridge. Actually, they both are, because in some ways it's just a matter of changing. If I change the w, I can get one or the other. But in this particular version, we have an adapted version of the Brownian bridge, or the Penn-Brownian motion, and we have a little bit of problem. It's the improper integral, right? As I approach 1, right? But in fact, the limit gives me the right thing. In this particular version, actually, it gets me to x1 at the 1. So actually, the limit almost surely, right? Because it is random, and it's adapted. So there does exist a solution of this type. And we didn't do it quite the same way. We weren't actually able to separate the two equations that were going forwards and backwards, but we were able to guess the right answer really from the case where we could. Okay. So here's another idea that we have here, that if I wanted to get this adapted solution, instead of looking at the problem where the trajectory is driven by Brownian motion, what if I took instead the sort of standard Brownian bridge? So this is the Brownian bridge where when t equals 0, it's 0, and when t equals 1, it's 0. But it also has this noisy component, and kind of on the average, when you're at any t in the middle, it's just kind of like Brownian motion in a way. These two things kind of balance each other. So what if I use that instead in my trajectory equation? Use that process. And then I have my Euler-Lagrange equation, which is that the u should be constant. And I can have my endpoint values. And I get this solution, which is exactly, so this is just solving the same way, right? I ended up with that value in 1, but in this case, even though it's adapted, y1 is always 0. So. And so all we have then is we have this drift term, but it takes us, instead of having the line that goes from 0 to 0, we can have it go from anywhere to anywhere else. That's what the first part does once you can zero out the y1. And the other part is the noise part, which is kind of like the Brownian motion. It's actually the best substitute we have for Brownian motion if we're going to also tie the ends. So that means that this is sort of the question that I've investigating but haven't been able to answer is that how often can we do this? How often can we do this? How often can we, if we have a problem of some kind, an optimization problem, well, the Euler-Lagrange equation will give us probably an anticipating solution to that with too much information, or requiring too much information. But how can we find, then at that point, can we find an appropriate process, like a Brownian bridge, that we can substitute for the noise in that problem, in the trajectory? And so the first part, what we're solving for the relationship of the u, and the second part, we're going to try to find an appropriate noise term that we could replace for the Brownian motion but still make it adapted and satisfy some sort of bounding conditions. So how far can we extend this? Well, I don't know very much yet, but this is the motivation for this question. And sort of as an aside here, that one of the things that became kind of apparent is that if I'm going to be able to use this other noise, I want to be able to simulate it, or I want to be able to find that noise in some way. And it's a difficult equation to solve because, as I noted before, well, as I approach 1, the integral becomes improper, or the idea is that we have a singularity at 1, right? There's this term is going to blow up as I get close to 1. So this makes a problem for numerical simulation because if I use like the Euler method, the size of the jumps are suddenly going to get huge as I get close to 1, right? So, and that's actually maybe kind of the way the whole thing works. If you don't have the Brownian motion is that if I get very far away from my target, it turns up the countervailing drift force and pushes it back towards the target really hard. And in order to do that in every case, it means that so if you look at this case, I want to get back to 0. So if x of t gets very big, I'm going to have to divide by I'm going to have to make a very big correction in the other direction, right? As I approach my end point. So that's what it does. It makes a big correction at the end. Well, so this makes it a difficult simulation problem, but this is a result that I got with a student, Uchan Sarvardhan, and actually this is a special case of it for this problem, and that is that we can fix sort of H star as just sort of a general sort of scale for this simulation. And what we're going to do is we're going to take step sizes. H star is less than 1, so the smaller H star is, the bigger this value is. The step sizes, well, the node points where we're cutting it are going to get never quite reach 1, but they're going to get closer and closer together. Right? The step sizes get smaller and smaller as I approach. So I'm adapting the step sizes so that I get, and so in fact I can have an infinite number of steps and never quite make it to 1, but I'll get it arbitrarily close to 1. By taking those sizes of steps, and if I wanted to make everything more fine, I would just start with a smaller H star. That would produce a smaller, closer result all the way down the line, but closer and closer still as I get close to 1. And so using the Euler algorithm, it's just I'm going to update the value by taking the derivative, that drift term times the t increment, and because it's we have the Brownian term, but I also want to add an increment of the Brownian motion, and so if I define an algorithm using these step sizes and look at the error between the actual solution and the algorithm computed values, our result was that we can find actually there is a kind of universal constant for given the interval that where the L2 norm of the with respect to the probability, right, or the variance of that is bounded like so that this is the norm squared, L2 norm squared, so it's like H star squared. So the L2 norm is like H star. So that we can actually decrease H star and know that we're getting better, more accurate. So there is a fairly efficient algorithm using this adaptation of step size that will get us there. This is actually independent of the total number of steps. So however far you want to run it, this estimate will work for all those steps. What happens with the Brownian bridge is that the variance is biggest in the middle. When you're pinned at the ends, there's not much variance at all. So you really have most of the error is in the middle when you use this method. If you took big steps, then suddenly you're at the problem. You gotta take smaller steps so you don't get onto the problem too quick. Okay, so we can do this the same sort of thing. This is example 2. This is the same idea as that I look at a little bit different process for the noise. Set up the problem that way. There is the solution for this process, and again I can use by changing what I'm using in the trajectory. I can use the Euler-Lagrange equations to find the solution. But I kind of have to know the right thing to put in there. So I mentioned that we can take a calculus of variations problem and we can add some constraints. And one of the ways that we might do that is to look at a more general sort of term in this position, right? Not just U, I can look at something more general. And the idea there would be to, well, still call that V, and then but add another equation onto there. And I'm going to maybe kind of go through this kind of quickly, but that's kind of the basic idea how we take a more general control problem and formulate it as a calculation of variations problem. So we go the other way, and so in doing that though we actually increase the number of dimensions that we have to look at. And so this is a multi-dimensional problem. And we can define the functional in terms of those. We use here's the constraint occurring in here, right? So we added a variable to make this, the multiplier, right? To make this into a constraint. And so we get an inversion of the Euler-Lagrange equation. We get transversality conditions that all come into play. Those produce additional equations, and so I'm going to try to jump to the result here. So this is what the Euler-Lagrange equation would look like in this kind of case. That functional g is going to change this result here and affect these values too. But we have a similar sort of problem. We have the Euler-Lagrange equation, we have the trajectory, which now has a little bit more general kind of values. All right, I bring this up because that does allow us to deal with what's known as the linear regulator problem, the linear quadratic, right? So we have a functional which just quadratic in u and x, quadratic in the end condition, and the function that's controlling the where the control goes in, that's the drift part here, is now a linear function of x. It's linear in x and u, right? Not necessarily in t. And we require at least that r sub t be bigger than 0. So if r is equal to 1 and all the other stuff is 0, then that's our original problem, right? So, and if we didn't have this term, just had the beta equal to 1, that would be our original problem. And so because this is more complicated, right? This is more complicated. We have this kind of our constraint problem. We get the equation and we can come up with a solution. You notice that again, it depends on n values. Right? We're going to have to solve it for n values. And so we can represent the solution this way. But again, I wanted to point out the dependence. The computations here are going to be coming from the right boundary condition, which will involve the u part here, the second component. And so u sub a would have to be determined based on what happened at the right boundary. And so this is in general the anticipating version of the solution. But so here's the question: is how do I change this to make an adapted solution like that? I'm leaving that as an exercise, I guess. But even with the anticipated problem, or if I can find another process that will make it convert it into an adaptive process, but this functional, there is a computational problem here. Is that how do we find solutions of Euler-Lagrange equations that have this kind of form, right? That come from the linear quadratic equations, and the answer is that this is known in the calculus of variations, and I actually worked on some time ago on this part of it with John Gregory, who was here. And what we have here is we have an algorithm that's really a three-term recurrence, or you can think of it as it's a matrix multiplied times the vectors of the y's. And the matrix, if you look at what's involved there, is tridiagonal, and so it depends on being able to actually invert m. But once we do that, the algorithm is this matrix, this tridiagonal matrix multiplied times the y. It's got to equal this, the negative of psi sub k. And this depends on the coefficient functions, but also the diffusion term. So that's where the noise part gets injected into this thing. So if I know exactly if I'm using Brownian motion, then in general this process is going to give me the solution because of the n values. Right? We have the n values, particularly the value at the right plane. It's going to give me an anticipating solution. But if I had the right kind of noise term in my problem, that I might be able to, like the Brownian bridge, I still might be able to find a non-anticipating, an adaptive solution. And this very directly tells me how to take that particular set of noise, particular realization of the noise, and give me what will be the solution will look like for that particular one. So not only is this something that will work on average, will give me the right thing, but it actually will tell me what I should choose for a particular noise. So if I can invert the n, and if I can do that, then I just have to apply it to the noise parts, and get my solution out of it. So that's a computational reason why we want to be able to use this calculation variations approach, because of this particular type of numerical solution we get. And in the work with John Gregory, we showed something about, in the case where we have the anticipating version with Brownian motion in there, the error in using this kind of approximate algorithm can be controlled pretty well. Really. So, but the L2 norm as small as h to the 3 halves, that's not bad. So. That's it for our, maybe went a little bit longer than I should have, but I got it before 4. Okay, thanks.
Do you have any questions for Andy?
Yes.
Very interesting talk, but I don't understand a lot of it. I talk about in my class a lot of Brownian motion and diffusion.
Mm-hmm.
How are you going to relate to maybe a chemist who does not really know a lot of math?
Right. So the idea, one of the important ideas of using Brownian motion in particular is that it provides it's kind of a particular type of noise that you might expect, and in fact, if it's a way of injecting noise that has the kind of characteristics of Brownian motion. That is, that it's that the increment, first of all, that the increments are independent. So what does that mean? It means that if I look at between 2 times here, s less than t. So if I look at what I've gotten up to time 0 up to time s, and then I go from time s to time t, that these 2 things are statistically independent of each other. So what it represents then is a kind of noise that really doesn't the white noise doesn't really have any kind of memory, right? It doesn't care what happened before. It does its own thing, right? So it represents a particular kind of noise that you might see in a system, and it's also very regular in that the variance is consistent. So it's a particular version from which we can derive other kinds of noises. And so one of the ways we might derive other noise is that we might vary it with time. So or if you look at that I might take some function of time, and so that I have, by changing this function over time, I can change the intensity of the noise at different points. Mm-hmm. But the Brownian motion has sort of a standard intensity that we can. It's a useful theoretical construct that allows us to look at lots of different kinds of problems. Mm-hmm. And so one of our concerns is certainly that we were able to look at problems where we can vary that intensity, right? Or in terms of volatility, right? You might talk about it in the financial approach. I've been looking at this one-dimensional Brownian motion, and in chemistry and physics and biology, more often looking at kind of Brownian motion that's over some surface or some space, perhaps. But it's also true that this is the right thing to look at, because you can just look at 2 independent copies of Brownian motion, or 3 copies, and let those run, and that will give you the same kind of characteristics in multi-dimensions. So it does scale up to the more dimensions to recognize things.
Any other questions? Okay, let's thank Randy again.